Welcome to our webinar today, which goes out to our customers, students, interested engineers, and last but not least, our competition. My name is Emilio Meza, and I'm your moderator for today's webinar, Improve Performance by 25% while reducing cost in wind converters. High-power wind turbines call for higher power converters. Meet these demands with the new SKiiP 4, which achieves a 25% power improvement. Today, Marco Hansberg reveals improvements to the field-proven sintered SKiiP 4. He explains how we achieve this through the high-performance cooler and optimized chipsets. Marco joined Semikron in 2017 as the Senior Manager, Product Management, IPM, and Electronics. His background is research and development of frequency converters in power electronics from 30 watts to 1.5 megawatts. With a background of power electronics, circuit design, pulse width modulation, and control software for drives, he has been managing application engineering activities for industrial IGBT and IPM modules, as well as high voltage IHM traction modules for 18 years. Today, his focus is the commercial viability, planning, and conceptualizing the next generation of intelligent power modules and electronic products for Semikron. Enjoy the webinar. Marco, the floor is yours.
Oh, thank you, Emiliano, for the kind introduction here. And a warm welcome from Düsseldorf to the rest of the world. Thank you for your great interest here that I can monitor here. I would like today to talk about the SKiiP 4 and the latest findings that we have. Among that is the SKiiP 4 and the high performance cooler here, but let me go through point by point through the agenda here. So first, I would like to give a bit an overview about the SKiiP. What is a SKiiP? What are the features of the actual SKiiP 4? What is the highlight in the reliability? And what is the specific solution that we have found here to create a high performance cooling? And also, I would like to talk about generator and grid side optimization of chip sizing. And of course, finally, an outlook when these new devices will be available. Yeah, for those who might not be entirely familiar with the portfolio of Semikron, I would like to give a brief overview just to give an orientation. So what kind of product range we are talking here and what is the product family. Well, you see that Semikron is a manufacturer of a lot of bipolar components here, as well as IGBT modules here, as well as a complete comprehensive range of IGBT drivers. And here at the upper end of the power, we find our highly integrated intelligent power modules dedicated for the industrial and also for the wind applications. Yeah, this SKiiP integrated solution is what we see here on this slide. First, we see that it is a kind of modular concept that we have here. On this left side, you see that this is the elementary half bridge construction. Each half bridge contains a current sensor, and these half bridges are put together here to form the power stage of the module. On top of the IPM, there is the driver circuitry that is covered here by this white cover. So we have a complete solution here containing the power stage, the driver, the interface. The whole SKiiP 4 IPM is safety isolated. We have a CAN bus feature here that I'm going to explain later. And of course, lots of customized functionalities that I'm going to explain later. Let's look a bit more deeply into the SKiiP 4, and let's start from the bottom. So I start here from the very bottom where you see the substrate of the SKiiP 4. Here on the substrate, you find a unique technology that Semikron has introduced to the market. It is the sintering die attach. I'm going to speak about that further. So these substrates here, these DCBs, you find all the chips on that. Then you have, of course, the housing here. I mentioned already the precision compensated current sensor. On top of that, we have all the laminar structure of the DC link, the DC plus and the DC minus, as well as the AC output bus bar here, all in a very laminated way, which means the internal inductance, strain inductance of such a half bridge is extremely low. Yeah, so we are talking here about typically something like 5 nanohenry. We are using high performance thermal interface material here in order to reduce thermal resistance throughout the entire construction of the module. One of the highlights that I'm going to talk further, because that will turn out to be a real advantage, is the baseplate-less design of the whole module, which gives us a specific advantage for water-cooled application. Yeah, from interface point of view, we have this kind of standardized SKiiP interface here, where you have all signals to switch the IPM available, as well as the output current information, voltage sensor information, the CAN bus interface. Yeah, they are all here electrically available through this connector. However, we have indeed several customers that prefer a direct fiber optical link connection to this high power module. For those customers, we have developed a kind of plug-on interface for the fiber optical connection. Yeah, the driver is one of the core elements of the SKiiP4. So what we can see here, the fundamental function here is the safety isolation from the primary side to the secondary side. This is something we are facilitating here with transformers. So it's a very reliable, a very robust separation of signals, and we can reach really very high isolation and safety requirements here. Then you see that it is a typical dual channel. So we have one complete driver for the top side, and we have another driver for the bottom side. And those two independent drivers are connected here on the primary side through this interface. The whole driver here is a digital driver. That means we have a dedicated chipset here. This is we have an own department that is developing the ASICs for the driver here, and these ASICs are highly integrated components where the entire functionality of the driver is implemented into, and it only requires a very small amount of additional components to facilitate the operation. Of course, the driver must drive, but it must also safely protect the IGBTs here. And that is something that is also highly adjustable, first from customer side, yes, through the CAN interface that I'm going to explain later, but also from our side, from factory side. So Semikron delivers lots of modifications for drivers to fit into specific application conditions. Yeah, as I mentioned, we have a kind of modem here. So we have a digital transmission of signals. So we are really talking forth and back, primary to secondary. So we know perfectly what is the condition of the half bridge, of the power stage. We are providing this information, of course, immediately through an error machine, but also it is available through the CAN interface, and, for example, can be used as a monitoring or tracking function. The CAN bus connectivity, as I've mentioned, looks from surface like this. So the application for this CAN bus runs on a standard equipment like it is shown here. And it is possible to make configurations at any time to the SKiiP4 to make parameterization of limits, for example, or to read out errors, or to track temperatures, yeah, and lots of other electrical thermal parameters is possible. get in touch with us for your specific problem. Most of them can be handled by the standard software, but of course we have options here to tailor make the digital driver for your applications as much as possible. Now, since we have talked about the interface, let's come to the device itself. Typically, we are talking about folds here. So one fold is one of the half bridges that I have introduced. A three-fold consists of 3 of those half bridges mounted on the heatsink here. And you see we have 3 different types available: 3-fold, 4-fold, and the most performing 6-fold SKiiP that we have here. And those are the water-cooled solutions. And here in the second row, you find the air-cooled solution. Of course, the water-cooled solutions are the more performing ones. And the SKiiP 4 is available in 1200 volt as well as in 1700 volt. Yeah, that brings me to the most important part of the SKiiP. Why the SKiiP 4 is so attractive and so widely used in the application field of wind turbines. Here, reliability and long-term robustness is very, very important. And I would like to show some of the most important features that we have. Let us start from the left side here. So first, the die attach. That is the connection between the bottom side, the back side of the chip, and the top side of the ceramic substrate. Here, the SKiiP 4 uniquely in the market is using silver sintering layer here that is much more robust and much more reliable than a simple soldering connection like it is used in many standard motor drive applications. Well, especially this layer needs to survive the low frequency, high temperature swing during a low frequency operation of, for example, a generator side converter. So the sintering, the sintered connection is one essential ingredient in order to reach the reliability that typically for a long-lasting operation of 20 or more years for a wind turbine is necessary. Coming to the die connection here, since we have the sintering contact below the chip, yeah, the bonding here can be the classical aluminium wire bonding, or in case it is really necessary, we have optionally a technology in-house that is a cladded aluminium copper bonding that is basically a copper bond that is entirely covered with aluminium, so that the interconnection between the bond and the chip is done by the aluminium. That allows us to reach another higher degree of reliability if that is requested. So far, the aluminium bond wire has shown sufficient performance to the needs of the typical wind turbine application. The terminal connection, and that is a real unique construction. You see, we have a really multi-finger contact here. Yeah, so that what I'm showing here now with my pointer is a DC link connection. This DC link signal is connected to the substrate here through a multi-finger contact. That has a huge advantage because it provides a very low strobe inductance. It offers like an additional layer in the construction of an inside of a module, because typically you have only a substrate plus a bonding in order to find all traces from the input to the output of a module. Here, with this additional layer, we bring the DC link signal to each point of the substrate very homogeneously in a very balanced inductive way here. And that is one of the advantages that we will use further here in this presentation. Because out of this very balanced construction, we can say that the chips are evenly stressed, and that means we have a very wide safe operating area, and the thermal loss distribution is very well controlled. here that are real advantages of such a construction within inside laminar busbar structure. Coming to the fourth point that I would like to mention here in this presentation, that is the heatsink interface. I have mentioned already that we have a base plate-less design here. Yeah, and such a base plate-less design in conjunction with a high performance cooler, and that is what I'm going to explain next, yeah, can provide unprecedented thermal performance. The interface here is just made by a very thin 15 to 18 micrometer, very specific thermal compound material, yeah, that we are applying here in a very, very controlled way in a clean room atmosphere. I'm going to explain now the high performance cooler, and that is an innovation that we have been working on already quite for some while. And in this image, you can see that just below the substrates here of the SKiiP, we have this pin-fin structure that makes the cooling so efficient. Let me go a bit through the history of that. So what we're having today as a standard water-cooled system, that is on this left image here. The water cooling channels here form a kind of star that already increases the surface contact between the aluminum and the coolant. So that is very good, actually, for the thermal resistance. But when we see the substrate, which is located here on the top of the water cooler, we see that the chips, they sometimes have a longer path through the aluminium here. That means the aluminium starts to become a contributor to the thermal resistance, and that makes this structure, of course, much superior than a water-cooled solution, than an air-cooled solution. Pardon, yeah. But we see that we need to bring in some improvement, and that has been consequently made by the high-performance cooler. So the first thing is we are benefiting very much from the inner construction of the SKiiP that is pressing the substrate very homogeneously to the surface of the heat sinks, to the very thin thermal interface material. And then in this kind of construction, the thickness of the aluminium till the water is reached has been optimized to a real minimum. So that is now a complete mechatronical construction, a complete optimization of the system has been done. The same is valid, of course, for the size, the number, the geometry here of the pin fins that are used in the water channel. Yeah, so lots of numerical simulations have been done, lots of tests have been verified in order to improve this very sensitive interface. And of course, the base plate-less construction here brings another important advantage in here, because a base plate here would not be helpful at all. Typically, a base plate of a base-plated module would be able to spread the heat a little bit in order to pass with the heat to the water, to the coolant through a larger surface. Here we already have the maximum surface available. Yeah, that means we don't need an additional copper that in this case would only add an additional thermal layer. On the right side, we have not opened this module. I think everyone here in this round is familiar with such kind of constructions. This kind of base-plated module, of course, we should not forget, typically in a classical module construction, the bottom side of the ceramic substrate is soldered to the copper, to this large copper base plate. But such large solder joints also have an aging effect. Yeah, that is what we all know as a thermal cycling effect. With this thermal cycling effect of this solder connection between the ceramic substrate and the base plate, we have another bottleneck in a classical module construction that we have completely eliminated by the base plate construction, a baseplate-less construction of the SKiiP. So 2 additional thermal layers have been omitted in this new construction. So no additional copper, and also this solder layer is not present in this construction. And that makes it very, very efficient. And let me show the results here of our measurements internally. So we have done a real evaluation test with an inverter test. We have used the conditions that you can find here on the left, in the left corner. So that are very, let's say, classical standard conditions here. And you see in the gray curve, yeah, you see the junction, the maximum junction temperature, yeah, as a function of the output phase current that is delivered under these conditions mentioned here. And the classical star type profile that I have shown, that was on the very left side of the previous presentation, shows that here at the range of something like 1550 amps RMS, we are already reaching the 150 degrees of junction temperature. If we do the same thing here with the SKiiP on a new high-performance cooler, we can immediately see that 25% higher output current is possible here at that simulation. And that is an amazing result here that, of course, has a very big impact on the cost per performance of such a new SKiiP on the high-performance cooler. So here we also have reached significant improvements for the cost per performance. So then let us talk about what we could do more inside the SKiiP after we have resolved the cooling topic here. Well, typically, more than 2/3 of the applications for a classical SKiiP 4 is in the wind converter market. So SKiiPs have always been dominating this market, and with the new technology here, we even give some more degrees of freedom to the designers, because I have already explained. We have the flexibility here due to the very homogeneous and low stray inductance inside the module on the DBC, which means we can also tailor-made chip sizes. Especially, it is well known that Semikron is manufacturing Call diode, which are unrivaled for the cosmic ray robustness. Here, these diodes here we can tailor-made in order to satisfy the 2 very different needs that we have in a typical wind converter application. Because on the left side here, we have on the generator side a typical requirement to operate at low frequencies, yeah, and typically at high voltages of the generators. So that means if we do the simulation for that, we immediately understand that power loss simulation results in the fact that the diode here is the bottleneck of the application. The diode is the bottleneck to reach the performance and the reliability that is needed in order for the long-term operation. This high temperature ripple we can of course tackle by putting more diode inside, which means a generator side optimized SKiiP 4 would typically contain a bigger surface of the diode, because that is much more stressed. On the other side, when we go to the grid side converter, the requirement is different. Here, typically, customers strive for a total cost optimization and try to reduce the output filter size as much as possible. That means a high switching frequency would be beneficial for that part of the application. This can be easily facilitated by optimizing the size of the diode. We know that the smaller the diode is, the lower also the turn-on losses can be, because the recovery of the diode impacts turn-on losses of the IGBT. So also here we can undergo a certain optimization of chip sizes to each other, and that is exactly what we can do here. So we can provide this extra performance to the IGBT here and allow the operation at higher switching frequencies. But there's a very difficult question to answer here. What is the best size for a diode? And the answer is very simple. It depends probably on the individual setup of our customer's converter. Well, this is a little bit an example just to give you an overview, because there is no unique solution, and that is what I have said. So we have this flexibility with the SKiiP that typically commodity products do not offer. Here on the very left side, so that is this diagram shows 100% of the available space on the ceramic substrate. We can fill this to a certain degree with IGBT chips and also with diode chips. And that would be a typical setup for a standard grid converter site. But with this very fine granularity that we have to increase gradually the size of the diode versus the size of the IGBT, we can even come to very extreme cases. I'm not sure if anyone would use that. It's a module that definitely contains more diode surface than IGBT surface. But in fact, the reality will be probably something here in between, especially for the generator side. Please talk to us. Yeah, we have lots of possibilities here to tailor make the generator side SKiiP for you. Yeah, then let's see what else is available and what kind of configurations we can offer with this new SKiiP. Very standard. Our very standard idea is, of course, since there are so many wind turbines in the field that are indeed also already using the actual SKiiP 4, we could easily offer a retrofit upgrade with the high performance cooler. So of course, the standard SKiiPs and the standard configurations can be upgraded with the high performance cooler. So mechanically, and as you have seen, the interface is standardized. It's a very easy drop-in retrofit upgrade. Of course, other components need to be adjusted. But we have investigated further and have thought about making even a more compact construction with the SKiiPs here, because the SKiiP is known for compactness, and we can drive this idea further, because also the cabinet size is a very important factor nowadays in wind turbines. That means we have designed here double-sided coolers. Indeed, these are, in fact, two independent coolers that are attached to each other, but of course, not really physically attached. They are designed as one piece, but the cooling paths of both sides SKiiPs are clearly separate. And of course, multiple options here to enter and to exit with the water. Yeah, so the classical flow through, then this kind of vertical entrance here. Yeah, and this kind from the top entry. So everything here is possible, and we have seen lots of different constructions are here in the field. How to make let's say these kind of connections advantageously. One very important thing is, if we have two power stages connected to one cooler, we immediately omit another set of water connections. Yeah, that is of course a cost, but it is more a reliability topic that we should consider here. So we're minimizing the amount of water connectors to the system. And here on the right side, you can see a typical example how that could look like. That is something that we have developed here at Semikron in order to show a very compact solution how a complete phase lag could act here. So you see in the middle we have the high performance cooler, and on both sides we have the SKiiP 4 mounted. That has, let's say, has a lot of features here because we could consider that one of those SKiiPs is a generator side optimized SKiiP, and the other side is a grid side optimized SKiiP. That means they would most probably have more or less the same size. Typically, the generator side converter, if it is built with commodity products, we need more of those standard products here in order to have enough diode available. With this new flexibility that we have in this SKiiP, we can put the diodes here on cost of the IGBTs that are not so much needed for the generator side typically. Yeah, and we put the diode here into that compact package. On the other side, we optimize the same thing for the grid operation. That has another advantage because when you see in this concept study, the DC link construction would be located here on the bottom side. And that also means that there's a very short track from the generator input to the output to the grid. That means that has also a positive impact on the requirement of DC link capacitance probably. And also, it would also have an impact here on the amount of copper that is necessary for the construction of the DC link itself. It's a very interesting solution here. Even the handle here for let's say for a quick removal of the of this unit as a kind of service unit. So that is a very attractive concept here based on this highly robust SKiiP 4 product. Yeah, coming to the availability, we have already lots of pieces in field with our key customers here, and we are going to reach the mass production status of this kind of single-sided, so the standard SKiiP 4 in this month. And a little bit later, by the end of the second quarter here, these kind of double-sided solutions will be also available with mass production status. We have lots of variations already here in this because sometimes we are building the drivers specifically for our customers, yeah, with specific interfaces, with specific signal interfaces, levels, and so on. Please talk to us. We also have made versions that do not use a current sensor. So we have lots of possibilities here to address individual designs. How to play with the new SKiiP 4 and the new performance? Well, this is, you may see on the new SemiCell here, that is our web-based simulation platform. We have already prepared the full data sets for the 3-fold here and for the 4-fold and for a 6-fold. So you can completely simulate the performance of the new SKiiPs on high performance cooler with this new SemiCell 5 version here. Please play with that. It's a very interesting and amazing experience how much current suddenly is coming out of a SKiiP. Well, let me just briefly summarize what we have been talking about here now for like 35 minutes. The SKiiP 4 is the most reliable IPM solution for demanding applications. That comes through the sintering, so the whole construction Yeah, so the extreme environmental protection. So we have an extended 3K3 climatic range here. The SKiiP 4 has a field-proven outstanding robustness against environmental and mechanical stress. Indeed, besides the application in wind turbine converters, we have lots of traction applications, light traction, where also mechanical robustness and vibration stability play an important role in the field. Let me point out once more that Semikron is designing proprietary ASICs, highly integrated, highly functionality with a digital core. And these ASICs provide the degree of intelligence to the power modules and offer the flexibility in the configuration and parameterization of the SKiiP, including the CAN bus connectivity feature. The SKiiP 4 is available with a high performance cooler, and that boosts the power up to 25% by reducing the system costs. I'm not mentioning here the increase in compactness for the designs and the substantial improvement of cost per performance of this new SKiiP 4 on the high performance cooler. Yeah, the new double side mounted SKiiPs on the high performance coolers, they put a new reference here to inverter and converter compactness. Simulation tool is available. In the handout, the link should work. Otherwise, you can find that on the website. And the highlight here is the flexibility of the chip sizing for the different application cases that we have. Up to 50% higher diode area is possible in the new SKiiP 4 construction that makes a optimization for a generator side operation very easily possible. Well, that has been my presentation. Thank you very much for your interest and for joining this webinar. And I would like to hand over back to Emiliano.
Thank you very much for this wonderful presentation, Marco. For the viewers, I have just shared the PDF version of this presentation, so you can download that now. We have received some questions during your presentation that we can go through here. So I'll try to group these as best I can, but the first is the SKiiP 4 able to operate up to 1500 volts for, say, solar and energy storage?
Emiliano, yeah, that is something I have actually not mentioned in this presentation, but indeed, the 1500 volts is already part of today's isolation coordination that we have with the SKiiP. That means the package is capable to operate continuously at 1500 volts DC. Today we have already a specific device that is made for photovoltaic applications, so especially at the cold start, for, let's say, for a certain time limited duration, this 1500 volt is possible, and then when the maximum power point is reached, the voltage would then decrease to the 1300 volts, which are today the limit of the chip. But we are also working on the chips here, and I have not mentioned that. So, so we are in discussion with several chip manufacturers here to make a 2.3 or 2 kilovolt chip into the SKiiP 4, and then make the SKiiP suitable for this continuous 1500 volt DC operation. It will take maybe, let's say, 1 year, 1.5 years, yeah, to think further. Please keep track on the SKiiP 4. I will publish news as soon as we have them on this 2 or 2.3 kilovolt chip discussion.
Thank you. And I'll group these couple questions together. It's about the construction. So you had mentioned the construction with the multi-finger contacts, and for the connection of those multi-finger contacts to the substrate, what kind of connection technology do you use? But then also, what is the ceramic substrates that we have available for the SKiiP 4?
Oh, typically we are using a pressure contact here, because also these multiple finger contacts, they are used to press the substrate down to the heatsink. Yeah, and since we have on the DC side DC plus and DC minus, and also the AC side, those fingers, we can realize a very homogeneous pressure on the substrate to provide this very low thermal resistance to the surface of the heatsink. The substrate here is typically, it's an aluminum oxide substrate.
Okay, very good. And then looking at the cooling, so you had mentioned that SKiiP 4 is available with air cooling. And so what is the difference in the power rating between the air cooling and the liquid cooling?
So, basically, of course, the chip rating is the same, but the thermal constraint here, due to the reduced cooling performance of an air cooler, I would say is like at least 30% less for the air cooled, maybe even more for a standard. And if we compare the high performance cooler versus an air cooler, yeah, the air cooler is probably only a 30% or 40% performing solution compared with the high performance cooler.
Okay, and then comparing the new high performance cooler with the original SKiiP 4 cooler, how does the flow rate and the pressure drop compare to the original design?
Yeah, we have deliberately chosen the geometry and the structure of the pin fins in a way that this retrofit upgrade is possible. That means we have been very close to today's original flow rate versus pressure drop parameter of today's existing NEC 300, so the existing style profile cooler. It is, in fact, also trying to use the same flow rate. So typically, we can say it's 4 liter per fold per minute. Yeah, so which means a 4-fold would then best perform at like 16 liters per minute.
Okay, very good.
Does that answer the question?
I believe so, yes. And then we have another one here about the high performance cooler for other devices. So because this brings a advantage to the SKiiP 4, could this be used for other standard power modules?
Basically, yes, and it would also be, of course, beneficial. But the specific structure that we have in the SKiiP is that we don't have the base plate here. We don't have this additional solder layer here, and the cooler is really optimized in a way that the pin fins are only where also the chips are located. So it's a highly optimized overall mechanical structure here that allows us to extract a lot more than one can do with a standard base plated module. I would say there's, let's say, in the range of 20% probably that we can get more here.
Wow, that sounds like quite a bit. And then I'll ask one last question here. Is there a second source for these SKiiPs?
The SKiiP itself, of course, is a single source product. But the SKiiP is following a multiple sourcing approach. As you know, we have at least 3 manufacturing locations worldwide for the SKiiPs. So we are sharing this risk. Here we're distributing the risk, and of course for this cooler, I can clearly say we have more than 2 sources here available in order to secure our customers' supply here.
Very good. Marco, thank you very much. To the audience, thank you for joining the webinar today. I hope you enjoyed it and you could take away some useful information. This has been the first webinar of 2021. We look forward to seeing you in the future webinars throughout the year. Stay safe out there and have a great day.